thrust on a side. So for this, we need to use pressure as force over area. The force being the thrust, so when you cross multiply, you'll get thrust is equal to pressure by area. So that's the first thing you need to remember. Second thing is pressure in a liquid and a gas is given by the formula rho GH, where rho is the density, g is acceleration due to gravity, and the h value is the depth of the centre of gravity below the liquid's surface. And what you're going to do is just basically to calculate the thrust, it'll be rho GH multiplied by the area of the side that you're looking at in the question. So we'll start off really straightforwardly. It says calculate the thrust on the tank base if filled with water. So first off, we need to get the pressure. The pressure is rho GH. The density of water is 1000. G is 9.8. And the centre of gravity of the base is right at the bottom of the tank. So it's 50 centimetres down, so it's 0.5. So that's where we get the 1000 by 9.8 by 0.5. Then that pressure is acting on an area which is the base, so we need to get the area of the base, and that's 0.8 by 0.75, and that gives you a thrust there as that value. Now I'm going to do the other two possible thrusts as well. The thrust on the front face, which is also the thrust on the back face, and the thrust on either sides. So the next one, calculate the thrust on the front side of the tank, which would also be the thrust on the rear side of the tank. So first of all, pressure is rho GH. The centre of gravity of that front side, that flat surface that's vertical and closest to you, is halfway down. So it's only 25 centimetres down. So for the pressure, we have 1000 for water, 9.8 for gravity, and it's 25 centimetres, so 0.25. And we need to multiply that by the area of that front side. And that front side is 80 centimetres long, 50 centimetres high. So when you multiply it out, you get that value. Now before we pick up the final side, which is the right or the left hand side, think about where the centre of gravity is. It's halfway down, so the h value in rho GH will be 0.25. Water will be 1000, G will be 9.8, and then the area will be the area of the right hand side or the left hand side, which is 50 by 75, but in SI units. And there we go. So 0.25 down, and then the area of the side is 0.5 by 0.75. Okay, something a little bit more involved. So we have a triangular lamina, ABC, is immersed in a vertical position in water with its vertex A at the surface and its base parallel to the surface. If BC, the base, is 10 centimetres and the height of the triangle, that's the vertical line from A down to BC, is 7.5 centimetres, find the thrust on ABC due to the water. So thrust is pressure by area. The pressure is rho GH, it's in water, so that's 1000, G is 9.8, and what we need is where the centre of gravity of the triangle is. Now if you remember, the centre of gravity of the triangle is closer to the fatter side, and then if you were to draw a line from one vertex perpendicularly down to an opposite side, as is the case in the diagram, you have a vertical line from A down to the line BC. The centre of gravity breaks that line up in the ratio of 2:1. So what that means is the distance from A to the centre of gravity will be 2/3 of that vertical height. So that's why in the rho GH section of the second line in yellow, we have 2/3 multiplied by the vertical height. And then we multiply by the area, which is half the base by the perpendicular height, half of 10 by 7.5 in SI units or metres, and we get a tension equal to that. Now there's a second part of the question. It says if D and F are midpoints of AB and AC respectively, find the ratio of the thrust on ADF and the thrust on DBCF. Okay, so let's have a look at it. D and F are midpoints of AB, so D is there and F is there. What that means is we've got a triangle here on the top section where that height there, the vertical height, is half of the total vertical height, and the base there will be half of the total base. So the area of the top section immediately will be half of, that's going to be 5 centimetres, and that's half of 7.5, which is 3.75, isn't it? So there's a mistake there. And that would be the area. The thrust on this section here, the top one, What we need to do is say that it's in water, so you've got 1000 multiplied by G. And again, the center of gravity is closer towards where more of the mass is, so it's closer towards that red line. And the center of gravity is along that line, but it's at that position there. So it's 2/3 of that length below the surface, so in that position. So it's 2/3 of half of 0.75. So again, that value is wrong, but you get the idea. So that value then is the thrust on ADF. All right. Now, this last piece is wrong. We have the thrust on ADF, so that's the top bit. And this thing here is the thrust on the whole lot. But we need to write it underneath the line as the thrust of that section there, which is a trapezium. And to get the thrust on that side, or that section, we're going to take the thrust on all of it, and we're going to subtract off the thrust on the top section there. So actually, underneath the line, we change that, we should have minus 0.1725. Again, this value and that value are technically incorrect because that's not half of 0.75. And you just work out the ratio and it'll work out for you. Okay, the final example. This is a Leaving Cert question. I think it was 1990 or something like that. It shouldn't have been asked because it's over complicated based on what the Leaving Cert course should be. So we have a closed tank in the shape of a cube of side √2. So √2, √2, √2, and √2. 45-degree angles there and there. It's half filled with water and half filled with oil of relative density 1.2. So the density of the oil is 1,200. Density of water is 1,000. Now what I've done is I've put a dotted line in there, and we know that if it's half filled with one and the other and they don't mix, the less dense one will go on top. So the water ends out on top and the oil ends out on the end. It said then it's tilted about one edge until those angles are 45. Grand, find the thrust on one of the vertical faces of the tank. So we're looking at the thrust on those, if the oil and water are not mixed. Now, if they're mixed, it's a different question altogether, but this one shouldn't be asked. I'm still going to go through it though. So remember that the thrust is equal to pressure by area, and in this case, because we have two different substances, one on top and one on below, the total thrust will be the thrust caused by the liquid on top plus the thrust caused by the liquid on the bottom. So T1 plus T2. Now, T1 is fairly straightforward. We know the center of gravity is somewhere there. You could use Pythagoras. Look, √2, √2, that's a right angle. That will work out as a length of 2, I think, and then you get that vertical height there as well. I think that works out as 1. So that means that the center of gravity there is 2/3 of the way down. What you could use then is the thrust is equal to rho GH by A, get the area of that, get the height, the density is equal to 1,000. The problem exists for the bottom section. So when you're dealing with the pressure on the bottom section, the pressure on the bottom section is caused by the oil, but there's also water pushing down on it, and that needs to be factored in. And this is something a lot of people didn't spot when the question came up. So let's have a look at the solution. Calculate the lengths, look, 1, 1. And what we're going to do is look at the thrust, which is the thrust on top plus the thrust on the bottom. And the way Dominic has done it there is he's looked at the pressure acting on the top section and the pressure acting on the bottom section as P1 and P2 respectively. So the top we have water by G, and it's 2/3 down because the whole length is 1 meter, so that's 66.66 centimeters. The pressure at 2 though is the pressure on the bottom. The center of gravity is there, so if you were to just take the oil, you'd have 1,200 for the density of that by G by 1/3 of the way down there. But the thing is, there's pressure due to the liquid on top, and the liquid on top has a vertical height there of 1. So that's why you have 1,000, the water, with a vertical height of 1 from the point A up there to where the two substances meet, and you have to factor in the pressure caused by that on the oil below it. So when you add the two of those together, you get that pressure. All right, so he's multiplied that out, 2,000 G/3, that's that, multiplied by the area. Area is half the base by the perpendicular height. Do the same for the one on the bottom, half the base by the perpendicular height, add them, and you get 6,200 G/3 newtons. And that's the last example. I'd suggest doing plenty of